Rivets or screws? A simple question, a simple decision point. But when you're designing a piece of equipment meant to bring comfort to millions of people, these choices add up. Hey, I'm Herman, the guy putting together these videos. Today, we're going to be following engineers Bill, Mike, and Caleb as we delve into just some of the engineering turning points that make a quality HVAC unit. From component selection to logic design, manufacturing hurdles, and life beyond the assembly line, we'll explain why and how we do what we do.
There are envelopes that need to be pushed and boundaries that need to be explored.
And hopefully we can make the industry come a long way from where it is today.
So we were always involved with the kitchen ventilation business and makeup air business, but we always knew there was something missing. Most people are used to dealing with all kinds of problems with their RTUs, whether it's belts breaking, refrigerant leaks. The average lifespan of that basic RTU is 12 years. That wasn't sufficient to us. And on the flip side, the high-end equipment was very expensive and very complex. The sequence of operations were very complex. So we took a step back, looked at all these factors, and wanted to create a high-quality, simple unit that lasted the lifetime of the building. Every single component had to meet that threshold standard. Will this component last 25 years? That's a simple question. It's very hard to answer, but it's a simple question and a simple starting point. And that's how Paragon was born.
Shortly after I started, I came out in the lab and saw the very first prototype, which pretty much consisted of some sheet metal design and a lot of concepts that are still used and others that are very long gone.
You have three primary drivers of energy: the outdoor fans, the indoor fan, and the compressor. So we had all those in mind, making decisions on these components that would bring the overall energy consumption down while not sacrificing performance.
For the compressors, we had three options. There's your on-off compressor, right? That just, you send power to it, it runs at one speed. You take power off, it shuts down. Then you have your digital scroll compressors, where these compressors always have power, and they just disengaged the compression scrolls at various rates. And by doing that, you can change the amount of refrigerant flow. This is more efficient than on and off, but it's not as efficient as actually slowing down the compressor, varying the speed of the compressor to achieve the desired flow rates, refrigeration flow rates that were needed for your design. So with that in mind, we were looking for the highest efficiency components, right? So on-off compressors were out. Digital compressors were out. So at the time, there were really only two manufacturers that developed or had a design that could be scaled of variable scroll compressors that we could use.
There are different levels of quality suppliers out there, but there's only one best component that we can use. And it's our job to ensure that we're selecting the best quality components for our end users.
In this case, the efficiency, build quality, and reputation of the two manufacturers were neck and neck. But it's not really until you reach out to suppliers that you understand how they work and what a future relationship might look like. Do they communicate well? Are they reluctant to send you a sample to test out? These are all things to consider, and of course, there's the cost.
The market has an acceptable level of cost and price point, so we have to figure out a way to design a high-quality unit that the market will accept. So one of the first and most important decisions was deciding on that compressor. After that, some things came into better clarity. For example, we would have never used a TXV in place of an EEV. The EEV was almost mandated because of that variable speed compressor. Check valves in the system and accumulators, crankcase heaters, things like that. If we're going to go with this high quality compressor, we want to do everything possible to protect it.
Since the EEV is responsible for controlling superheat, this is one of the biggest safeguards in ensuring the compressor isn't exposed to liquid refrigerant. So let's cut into one so we can see how it works. The refrigerant flows in this direction and is metered by this needle. Moving the needle is a stepper motor. When we close the needle, it changes how much refrigerant flows through this orifice. So how accurate can we be? Well, in this valve, we have 2,500 steps of control between the needle being completely closed and completely open. So we can be extremely precise on how we meter refrigerant. Using these valves was one thing we got right from the get-go, but we weren't always so lucky.
So there were many examples during the design phase of, let's try this technology, or let's try that and see if it works. Some of those were just complete dead ends. We realized that right off the bat. For example, on our outdoor condensing fans, we tried to use an industry standard prop fan with a small motor. And we realized really quickly, with a high quality, high performance unit, the condensing coils end up having a little higher static pressure. What we found is those prop fans could not pull the air through those coils correctly, and basically led to higher operating pressures, which translated into higher energy use.
We start to look at other manufacturers, other equipment, and then you go, I wonder, this is used in this application, but it's really the same as what I'm trying to do.
We standardize on a high-end EC motor condensing fan, very low noise, and it made a world of difference for the overall unit performance.
Every single fan essentially has a VFD, a variable frequency drive, that's tuned to that specific motor in that housing. And what that does is it allows us to use the most efficient combination of propeller, motor, and housing. There's static blades on the leading edge of those fans that help to straighten the airflow patterns, ultimately reducing the energy required. Anytime you can move air in a straight pattern, that's going to be the most efficient and most expected path of that airflow.
These kinds of designs are also seen in high-performance applications like gas turbine engines, including these noise-reducing chevrons, which are inspired by none other than Mother Nature.
Nature is very slow, but always gets things done, right? And does so in a very efficient manner. So by modeling their propellers off of whale fins, they were able to increase their efficiency by a couple percent. And it doesn't seem like much, but when you're moving that fan, maybe you have an application where it's 24 hours a day, 7 days a week, that 1% to 2% can save a lot of money for the end user.
At this point in my career, I've realized that belts are designed to fail. So if you have a belt-driven HVAC unit, you are actually designing failure into the unit. With direct drive blowers, there's no belt present, so you've eliminated that failure mode. We use a mixture of electronically commutated motors and high-efficiency AC motors to create the best possible energy and longevity solutions for the equipment. Not every 10 horsepower motor is created equally. There's different torque curves and different electrical characteristics, so we have to know that data, and we have to make good engineering judgment on which motor is going to perform best in this equipment.
Motor selection also depends on what type of fan we're using, and we can specify two designs. The first is centrifugal, meaning as the fan spins, the air is forced centrifugally around the fan. These fans are simple, affordable, and excellent at overcoming static pressure. The second is a mixed flow design. So what are we mixing? Well, a mixed flow wheel is part centrifugal and part axial, also forcing air longitudinally across the fan. Adding the axial element helps improve efficiency when moving high volumes of air. It also allows us to manufacture a more structurally robust wheel that we can spin faster and with less vibration. Thus, our mixed flow wheels can handle even higher static pressures. This is actually very important, partly due to what sits just upstream of these wheels.
If you look at a standard RTU versus Paragon, one major difference will be that indoor coil. If you look at Paragon, the coil is very thick. And you may ask, well, why do you need such a heavy-duty coil in this unit? And the answer is, as that air passes through that coil, there has to be enough residence time for the air to cool down and water to drop out of the air, moisture to drop out of the air. So it's thicker than a standard RTU because we process that outdoor air and remove that moisture correctly. With standard RTUs, the coils are thin, so they're only good at sensible loads. They're not good at handling latent loads. We didn't know what was going to happen in 2020, but we knew that outdoor air was going to become more prevalent over time. So we designed the unit on purpose to handle that outdoor air. Universally, if you want perfect conditions in a space, you have to handle that moisture correctly.
Aside from coil thickness, the fin density, fin pattern, tube diameter, and number of circuits are all optimized to draw moisture out of the air with the least possible static pressure penalty. Just upstream of this coil are the filters, and then you'll find the outdoor air damper, which controls just how much fresh air the unit will introduce.
We interviewed one producer of RTUs. We asked them why there was so much play in the damper blades. So when you say you're introducing X amount of outdoor air into a building, say it's 20% outdoor air, and those damper blades can actually move, how do you know you're actually delivering 20% outdoor air when the damper can fluctuate? So we selected a damper that didn't have that play in it. The gears are interlocking and they lock to a specific place, ensuring an exact amount of air quantity coming into the building.
This is just common sense engineering, and it applies to the small details too, with features like built-in lighting and convenience electrical, locating pins for the lesser used panels, and easy access doors with removable hinges for commonly accessed areas. So servicing these units is easy and you don't end up with 100 screws on the roof. And speaking of screws, we don't use them, at least not in the sheet metal construction that is. Instead we use rivets, which seal the unit better, provide better structural alignment, and never work themselves loose.
If you look at just the overall housing and the sheet metal in the unit, we use a G90 galvanized material. G90 means how thick that zinc coating is on the outside of the metal. So there's different grades of galvanized. G90 is one of the thicker coatings available, and that coating is important. You'll notice a lot of people will paint their equipment. And while that may look good up front and brand new, if you were to scratch that paint, that exposes that base metal to corrosion, and that corrosion will spread rapidly on the surface of the equipment. With galvanized material, it has a self-healing effect where it will oxidize over and actually cure or self-heal that scratch.
Eliminating the paint step reduces lead times by several days, so this is yet another common sense decision. Stainless steel is another material we use more selectively, like for our drain pans or our heating coils. In most RTUs, these are usually made of aluminized steel, which works but can corrode over time, allowing rust to take over. With a unit meant to last 20 plus years, stainless steel is just the way to go. And while we're here, it should be no surprise that our heating manifolds all modulate, and we even offer a split manifold design, which allows for extreme turndown ratios to deliver a precise discharge without having to cycle the heat on and off when demand is low.
Our primary focus was focusing on the sustainability of the equipment, making it as efficient as possible and as simplified as possible. So this is why we don't emphasize things like energy recovery ventilation. We wanted to make standard what we knew was a very reliable long-term technology and eliminate the things that cause complexity and problems for users. You can select the best components in the world, but that doesn't mean it's going to translate to the best HVAC unit in the world. It's important to ask yourself, do you really know what you're doing? And that's a very abstract question, but it's very important. If you don't know the details of something, you really won't know the outcome. So knowing the details of how something operates or how components work influence how the overall system works, and it influences the overall outcome of the system.
When you have a lot of components that are dependent on each other, but also modulating somewhat independently, you really have to understand what makes one component move. Right? So for an expansion valve, for example, what is going to drive my expansion valve to increase or decrease? It's superheat. On the flip side of that, superheat's measured at the exit of your indoor coil, right upstream of your compressor, which is also modulating, right? So how do you determine, okay, well, I don't want my compressor to fight my EEV, even though it's a far path to get from the discharge of the compressor. You have to go through a lot of components all the way to the expansion valve, but they still do have a little bit of a delayed effect. So understanding how to control that EEV so that's responsive to those changes, but also is capable of maintaining that superheat in an adequate amount of time is pretty critical.
Back in the 1920s, Russian-American engineer Nikolai Minorsky was researching automated ship control for the US Navy. Part of his research involved observing how a helmsman controlled a ship. So how does a human steer a ship? What kind of feedback do they take into account? And from this, he formally developed what we now call three-term control. Let me explain. Say we have a ship going straight in this course, and we wanted to turn and follow this other course. Naturally, we have to turn the rudder, but how much? Do we just turn as hard as we can? Probably not, then we'd overshoot a bunch. So how do we do this? Well, if our desired course is way different than our current one, we would turn a lot. But if it's just a little different, we would just turn a little bit. So how much we turn to correct our course is proportional to how much we need to correct, right? And that's our first term. Now, let's say we turn the ship this amount, but realize we're still not changing course very quickly. Maybe there's some wind or a current pushing the ship this way. At this rate, it will take a really long time to get back on course, or it might never happen. So, accounting for time, we steer some more. This is our second term, integral control. Now, finally, the ship is heading towards the right course at an acceptable rate. But we all know we're going to have to steer right to intercept this path, otherwise, we'd just cut right through it. In a way, we can look into the future, anticipate what will happen, and react accordingly. And this is our last term, derivative control. Three-term controllers, often referred to as PID controllers or PID loops, are used extensively in industrial applications. And while back in Minorsky's times this would be implemented as a complex feedback circuit, we can implement PID loops using software and the right inputs and outputs. For example, if, as Mike mentioned, we want to maintain a certain superheat, we would need a pressure and temperature sensor at the outlet of the evaporator, a way to control superheat, and the right PID loop to smoothly steer us towards our target. And just like wind and currents affected how the ship steered, conditions around our units changed constantly, so Paragon uses quite a few sensors to take all these variables into account in conjunction with finely tuned PID controls.
We have to control every one of these components in the system, and there's a specific guideline on every component on how you write that PID loop and how you control them, how many times you cycle them on and off in an hour, and how you bring oil back to the different systems. So all that has to be researched, and we have to do it the correct way to maintain that quality standard. And the end result is, if you do that correctly, that can translate to better indoor air quality because you can hold a very tight band in temperature, humidity, and CO2 levels in the space. So it starts at understanding the basic component, the details of that component, into a bigger assembly, and that can translate into the overall outcome into a building.
Refrigeration is very integral in my life here. But theory is just one portion of design. Practical application and empirical testing, that's the other half. You can design this in a lab for 10 years, throw a unit in real conditions, and learn things you wouldn't have even thought of in the lab environment. So let's get a unit out in the real world as soon as possible. Let's get that beta going. Let's get that data coming in, because a lot of the development and a lot of the unique corner cases that may exist will happen when you start introducing various environments, cold, hot, mix in between. The shoulder season's always a killer for refrigeration systems because it gets hot inside due to maybe internal demands, maybe it's nighttime and it was a really hot day, so now your thermal mass of your building's starting to really take an effect on the indoors. So you need it cool, but it's really cold outside. So how's the system gonna operate when you need a little bit of cooling and it's cold outside? So all of those start to come into play when you prototype units. That kind of goes hand in hand. It's almost like modulation on modulation, and you want to be as dynamic and flowing as possible to your conditions.
Writing the software and logic to achieve this flow state took years. And it's not just about extracting all the performance we can out of the system. It's also about making it last.
Just the compressor itself, we had to figure out how to throttle the compressor, how to ramp it up, how to slow it down, how to manage refrigerant in the off cycle. Believe it or not, what happens when the unit is off is almost just as important as what happens when the unit is running. One challenge with variable speed compressors is oil management, and how do you keep oil circulating through the system? How do you ensure that any oil that's in the system gets returned to the compressor? We do that through oil boost cycles, and we actually monitor the presence of oil with an oil level sensor. We have an operating envelope where we're looking at different conditions of the way the compressor is operating, and we will throttle that compressor to get into a safe range. So if pressures become too high or too low, we'll throttle that compressor to make sure that we do everything possible to keep the unit heating and cooling when it's most needed. In a standard RTU, you will not find any of this technology or any of these capabilities. This is a newer technology that we've standardized on, and we're changing the industry because of it.
One place we saw clear room for improvement were the electronics driving these units. I mean, sure, you can claim a unit is smart, but just how smart is it to run off-the-shelf PLCs designed to be mediocre at everything and stellar at nothing?
So instead of using an off-the-shelf PLC with someone else creating software where you may not know all the details of what's going on in there, we've brought all that in-house. We designed our own circuit board and our own software. So our engineering department can make changes very rapidly with that. All of our circuit boards are conformally coated to resist moisture. We designed circuits with through-hole mounts where we need some structure on that circuit instead of surface mount. Just looking at the most basic of components, whether it's a little terminal block or a little temperature sensor, if one of those components goes bad or has a problem with it, it can take the whole system down. So it's very important, even to the smallest component in the unit, to select the best component available. And then when you have a sensor that is involved with a critical operation of the unit, you want to plan for redundancy there. So in a lot of cases, we'll have two sensors measuring the same exact temperature, and if one were to fail, we'll revert back to that second one.
Our latest iteration incorporates a lot more sensors and a lot more logic to make sure all of these moving components are operating in harmony. Because if you start having them operate out of sync, you can cause some real issues with your efficiency. You can cause damage to components. You could cause premature failure. So by running through that design and iterative process to get to where we are now, we really have a much deeper understanding of where we were initially.
Nothing really happens overnight if you think about it. It's a gradual process, step by step. You always learn from where you're at now and where you want to be. So we practice that Japanese art of Kaizen, which means you make daily incremental improvements. And if you look at that over a long period of time, not only does it impact your entire company, but each and every product gets better each and every day through better quality and better process standards. If you're the quality manager for a company or quality director for a company, and you're producing thousands of products a day over multiple manufacturing centers, how are you by yourself going to maintain and manage quality? It would be impossible. Because of that fact, everyone has to be involved in improving quality. It's not one individual, it's everyone that touches that product along the way, whether it's engineering, sales, service, or production. Bob started this concept called quality at the source, which means that everyone takes personal responsibility for what they're doing. And we still practice this today after all these years of the company being in existence. It's been the most reliable source of quality that we have. Our quality team established something called a Brazing Academy. And basically what that is not only did we teach people how to braze, but we taught them why they were doing what they were doing. We showed them through theory and through practice why brazing was important and what was actually going on in that brazing process.
You know, a little bit of extra knowledge behind what they're doing just went so far, you know. Every single thing that they got wrong on the test, I mean, I'm going through with them every day or every other day. I'm walking back over and be like, hey, by the way.
Yeah, follow-ups.
Yep.
Those are critical.
Yeah.
We take all the components and we're actually cutting them apart so that we can verify the quality of the braze that we see for each of the individual components, looking at how is the fill, does it have clean, concave all the way through, is there any porosity or bubbles that we see, do we have lack of fill, and so we're looking at does that create a quality braze throughout the component.
At the end of the day, we had people graduate this program and I could tell on their faces they were very proud of this. When people take ownership of what they're doing and are proud of what they're doing, we think the results are better.
Not only did this Brazing Academy educate our technicians on how to make a better product, it also shed light for our quality team into how we can improve our brazing fixtures and which subassemblies made more sense to take off the line. These gradual process improvements are not just nice to have, they're a necessity when trying to raise that quality bar.
One task that we were challenged with was how to reduce the defects, internal defects of our weld quality, and also reduce the overall vibration of our wheels.
So this was attempt number 1.
Yeah, oh yeah, I didn't even know they had this one. Great. This fixture didn't really align any of the center components with each blade. It also limited us from using it during the welding process, so it only would fixture it when initially setting the blade position. With this in mind, we probably went a little too extreme the other way. Over-designed a solution that is very complex, a lot of moving parts, locking in each blade in multiple planes.
I mean, even looking at the complexity of this, it's not intuitive. I have to give you detailed instruction of how to use this device to put on a wheel, where we can look at something like this and you can see it's intuitive of how it matches up with the wheel currently on the robot, of you're placing it over and you're tightening it down. And so it's a much more simple process and it's a better product for them to use overall.
When you lock this fixture down onto the wheel, you're locking in every blade relative to the center hub. You're also applying pressure down on the top plate. And what this does is it concentrically aligns every blade in the same exact position every single time to the hub. So we know when we go to weld this wheel, these blades are going to be in the exact same location every time.
This is a great example of creating a quality process that is manufacturable.
These wheels create an enormous amount of vacuum inside the unit to maintain the required airflows, meaning if there are any leaks, untreated outdoor air would easily make its way into the building.
So something that's really simple but can be taken for granted and cause some major issues is how well these gaskets seal and the cuts on the gaskets themselves. So if they're not perpendicular to each other or the proper length, you can have water, air infiltration in through these doors or out from the unit. So we've actually implemented an automated gasket cutter and a kitting process that pre-cuts all this gasket for this specific door. So all of these pieces of gasket are cut on a station upstream to the exact length to ensure that there's a proper seal.
That's one thing I appreciate about our quality department. We get direct feedback from end users and our salespeople. For example, in this case, we got reports of leaking doors in the field, and these guys went to work with that data and came up with this solution. We realized we weren't cutting the gasket correctly, and we were stretching it in some cases. So they put some quality protocols around it, recommended some equipment to solve the problem, and now it's implemented. And that all happened very quickly. We can take an issue and convert it to an action really quickly. As you become more mature as a company, you go from an attitude of just getting it done, which is important, but then just getting it done correctly, and correctly every single time. This is a part of that process. I like to think of it as part of the nitty-gritty details of production. Wire routing was variable between all of our facilities. So we wanted to standardize on it so that if there was a problem in a field or was an electrical interference issue, we would all be consistent and we would know where the problem originated and how to solve it. That's what this does. This template here allows production to lay out the components on a board and make sure the wire routing is going to be correct to every one of those components.
Wires, circuit breakers, sensors, or even coils, compressors, motors, you name it. These are all parts and materials we acquire from different suppliers. So let's have a look at how we control quality when we weren't even there to produce the part in the first place.
Much of what we build is an assembly of procured parts. We rely on our supplier quality pretty heavily. One issue that we just found, they're actually testing these now. Some alignment pins in our wheel hubs that you just saw were out of spec. So the quality manager here ended up making some jigs just to validate that these pin locations were in the right position prior to welding the wheel and wasting all that time processing a defective part. It's so simple. Yep.
In order to track supplier defects, you need to both document and record what the defect is so it can be followed up properly. And so we started implementing these defective parts components bin really within the past year. People on the floor would say, I'm going to throw this part in the trash and not document. And now this has moved to truly documenting, getting it fixed, not ignoring any issue. If there's no consistency, if it's just a one-time issue on a low-cost component, then it's not necessarily something we would address. But if we see any trends, and that's what you're looking for in quality is trends.
How's that process been, the supplier non-conformances? Do they accept that data well?
I mean, we've seen it in the responsiveness from our suppliers improving significantly. Of suppliers we have sent issues to where we properly document, properly track, show them exactly what's going on, because ultimately we make our supplier better, which they like because then they're producing a better product, and then we also become better overall too. So it's correcting it even before it gets to us.
We do still perform checks on many supplier sub-assemblies, and sometimes these checks are even manufactured into the product before it leaves the supplier. Here's a good example of that with these coils.
We have worked with our suppliers to seal off the coils. You can notice here that there's a seal, it's brazed shut on this end, and on the opposite end you can see that there's a Schrader port. So our suppliers are sending the coils to us pressurized, and one of the first things that we do before we use the coil is to check to make sure there's a minimum amount of pressure inside the coil. If there's not pressure, we know that there's a potential leak in the coil. We know to take corrective action there. These are a critical component to us, so we want to make sure that if we do have a leak, we identify where it's happening, what process is causing that leak, and it's a way for us to grade supplier quality as well. If we detect X% of coils from one supplier is much higher than another supplier, we know to shift that volume away or issue corrective actions to the supplier causing those issues. Not only do we check pressure in the coils from the supplier, but we also check downstream and inside the total system on 100% of units. We use these to vacuum our equipment down, check for leaks, high pressure checks for structural issues with piping, medium pressure, we inject a tracer gas, helium, and we look for small leaks in the copper tubing. And then once it passes all that, we evacuate the system down to a 500 micron level before we fill it with refrigerant. And this equipment has programs in it for each specific unit to make sure that we do that correctly. If you tighten up a wire and the terminal block is tightened down on insulation, it won't conduct electricity correctly. So using that thermal imaging can help us identify those cases where we'll have a marginal connection or improper connection. We also look at all the coils to figure out if there's any dead circuits in the coils. All of these circuits in the coil will go back through the coil many times. It's possible that a supplier will raise these U-bends on, these return bends on the same ends of the coil, so that will be considered a dead circuit. The thermal imaging will help catch that problem.
We're building in automated testing. So what is automated testing? One of the checks that we have on a lot of our units is, let's make sure that all of our temperature sensors are operating correctly and wired in the correct location. Seems pretty straightforward, but there's a lot of little things like that that are simple in itself, but difficult when accumulated on a massive list. So if we can build in a system that no matter what, when this is ran, when the blowers ran, when the heaters ran, we're digitally recording all of those temperatures, making sure they're within a certain degrees of each other, making sure that your discharge sensor is wired to your discharge and installed in your discharge location. If we can automate that and let the individuals focus on the tasks that matter, then let's do that. Let's automate that process.
Something with automated testing is that sometimes people are hesitant to trust software. They'll say, how can I know that this is actually reading what it should? And we are actually doing both manual with software, so it's a double verification. You can see him going through and he was just measuring for leaks while it's prompting him on the screen to check for leaks. So it's not just software automated testing, but we're also having the manual user secondary verify without adding any extra time.
We 100% functional test our unit. So part of this automated testing requirement was, let's grab all that data, all that metadata, and upload it to our quality module, quality control module. And furthermore, let's make that accessible to tech support, to sales regions. So if there is an issue in the field, maybe associated with the install or application or something else, we'll be able to reference how that exact unit tested within our facility.
One of the things I ask any quality engineering candidate, what is your definition of quality? And I don't think there's one set definition, but what I can say is we define quality to be meeting and exceeding customer expectations. And there's a lot of other things that could be said, ensuring a product is built per specifications, that's often associated with quality, but really if you build it per specifications and your customer was expecting something else, to them that's a poor quality product.
With these big RTU producers, they produce to stock distributors, and then contractors go to these HVAC distributors and pull from stock for applications. So there's multiple levels between the producer of standard RTUs and the actual customer. With Captive Air, we specifically design and produce equipment for a specific application in mind. So we select our components, select the configurations to best serve that user.
Details like what kind of supply wheel to use, how much turndown is required, or the need for reheat are just some of the decisions to consider. And look, in a market full of one-size-fits-all units, we really do feel that one size fits none, at least not without making unnecessary compromises. So truly understanding the application and the customer's needs is critical to achieving a quality outcome. The same can be said for curbs. We don't just slap the same curb on each unit. Instead, we calculate airflow requirements for each and every adapter and design the right configuration for the rooftop. This makes retrofits a breeze with no surprises in the field. And the nice thing is we can still do all of this with extremely quick lead times, a benefit of having multiple manufacturing sites across the country.
When the unit's done being produced, at the end of the day, we load it onto our own trucks and we deliver it directly to job sites. We were forced to do that because of the trucking industry being a total disaster when it comes to shipping damage. Normal LTL shipments, there will be several different touch points for the equipment, cross-docking, loading, unloading multiple times before it gets to a job site. With our shipping fleet, we load it onto our trucks, our drivers deliver it to a job site and actually help unload it. So what that translates to is our application engineers work directly with users to design equipment. We produce it to those exact specs with the highest quality components. We then ship it to job sites directly with our fleet. Our service department then starts the unit up to our standards and specifications to make sure that equipment is operating correctly. We then monitor it on CastLink to make sure it's operating for the life of the equipment as it's intended to. That's what it takes to make users happy. That's what it takes to make our customers happy. Quality has to be built into the overall process, from the very first decision making for the application all the way through the longevity and the lifespan of the equipment. Everything in between has to have quality built into it. So in addition to CastLink, which is very powerful for looking at this equipment online, we have a direct service team, and those service members are on the ground reviewing this equipment all the time, and they give us direct feedback. Anyone in the company can pick up the phone and call me or the owner of the company, no questions asked, and say, hey, I've got a problem with this component. We got to look into this. That becomes our top priority for the day. We drop everything else we're working on and solve that problem. We do that no matter who's calling us, whether it's someone in manufacturing, sales, or service.
Having so much feedback throughout the life cycle of our products has resulted in special features like construction mode, which allows for the unit to start up while the building is under construction. This mode brings in 100% outside air, flushing the indoor environment from typical construction pollutants and speeding up dry times. We also offer what we call connected commissioning. This service is not just about whether the unit works. It's about squeezing every possible ounce of performance, comfort, and longevity year-round, something the industry isn't quite used to.
There's a knowledge gap that we have to close between us producing this high-quality equipment and customers actually seeing the value in it. I will say, though, talk to a lot of customers about this equipment, and I've had a lot of customer visits here and with customers. And as you explain and talk about the challenges that customers have with their buildings, whether it's high CO2 levels or high humidity levels, these problems exist in every application. And as the industry learns about Paragon technology, it's becoming more transparent that it is the right technology to solve these challenges.
Hopefully we can make the industry come a long way from where it is today. There's a lot of potential. There's so much more to gain. And hopefully, everyone stops a little bit to look back at where we've been so we can direct ourselves to where we're going.
Well, that was fun. Hey, if you made it this far, I just want to say thank you so much for sticking around. And if you didn't know, we have a growing library of videos on refrigeration, air quality, motors, controls, and other topics that may or may not interest you. So take a look, maybe leave us a comment, let us know what you'd like to see next, and hopefully we'll see you around next time.